Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
You know, there's a specific kind of arrogance in physics.
Oh, absolutely.
And I don't mean that in a bad way necessarily. It's a beautiful arrogance. It's this deep conviction that if we just stare at the blackboard long enough, if we just crunch the math hard enough, we can boil the entire chaotic mess of the universe down to one single line of code.
The famous God equation.
Right. The theory of everything. A single framework that explains, why the sky is blue, why black holes evaporate, and why you and I are conscious enough to sit here and talk about it.
It is the ultimate reductionist dream.
It really is. But for today's deep dive, we are digging into the text, the quest for a final theory of everything. And they think, well, the real story here isn't about that perfect equation. It's about the fact that we might have completely hit a wall.
A wall, or maybe a horizon. That is the big debate right now. Because, look, we've spent 400 years unifying things, taking separate phenomena and proving they're just different sides of the same coin. But now, we are stuck in what might literally be the deepest rut in the history of science.
And that is exactly what we are unpacking for you today. We aren't just doing some dry history lesson. We want to look at the actual breakdown.
The Great Schism.
Exactly. We've got general relativity on one side, quantum mechanics on the other, and they absolutely hate each other. Plus, we've got string theory, which promised to fix everything, but maybe got lost in its own math.
And then you get into the existential stuff.
Oh, yeah. Consciousness.
Yeah.
Gödel's incompleteness theorems, the actual limits of what the human brain can comprehend.
It forces you to step back and ask, is the universe actually a puzzle with a final, neat solution? Or are we just peeling an onion that has infinite layers?
That is the perfect way to set the mission for this deep dive. But let's look at the track record first, because that is where all this optimism comes from, right? If you look at the history of physics, it's effectively a history of things merging.
Yeah, we call it the drive toward unification. It basically kicks off with Newton in the 17th century. And everyone knows the whole apple falling from the tree story.
The classic physics myth.
Right. But the real breakthrough there wasn't just discovering gravity. It was the universality of it. Because before Newton, people actually thought objects on Earth and objects in the sky were governed by completely different rules.
Right, the Aristotelian idea.
Yeah.
The heavens were divine and perfect, and the Earth was, messy and corruptible. The moon didn't play by the same rules as an apple.
Exactly. And Newton completely smashed that. He proved that the moon is actually falling, just like the apple. It just have enough sideways motion, tangential velocity to keep missing the Earth as it falls. So suddenly you have one mechanical principle, one gravitational force governing the entire cosmos.
One law to rule them all.
Yeah.
And then you fast forward to the 19th century, and James Clerk Maxwell does the same thing.
With electromagnetism.
Yeah, before him you had electricity like lightning or static shocks, and you had magnetism, guiding compasses, totally separate things. Maxwell unifies them into a single electromagnetic force. And the craziest part, the cherry on top, is he realizes that light itself is just an electromagnetic wave.
It's just a brilliant winning streak for physics. And then Einstein comes along in the 20th century.
The ultimate merger.
Right. He unifies space and time into the fabric of space-time and shows that the geometry of that fabric is what determines gravity. Then, by the late 20th century, we get the Standard Model.
Which is where things start to get a bit sticky.
Well, yes and no. The Standard Model is incredible. Glashow, Salam, and Weinberg managed to unify the electromagnetic force with the weak nuclear force. We call it electroweak unification. And they incorporate the strong nuclear force, too.
So we basically have a periodic table of fundamental particles.
And it works beautifully. It is arguably the most precisely tested theory humans have ever created. But there is a massive catch.
It leaves out gravity.
Exactly. It leaves gravity totally out in the cold.
And this is where that schism happens, as you called it. It's the part of the source material that always blows my mind. We basically have two rule books for the universe.
And they refuse to talk to each other.
Right. You've got general relativity for the massive stuff. Stars, galaxies, black holes, smooth, continuous space-time. And then you have quantum mechanics for the tiny stuff. Atoms, quarks. But the quantum world is discrete. It's point-like, it's jumpy,
Yeah.
and they work perfectly in their own separate domains.
But if you try to combine them,
Total disaster.
total disaster.
But mechanically speaking, why? I mean, why can't we just take the gravity equations and add them to the quantum equations?
It comes down to something called renormalization. In quantum mechanics, we treat fundamental particles, like electrons, as zero-dimensional points. When you calculate the forces between them, you have to sum up all the infinite possible ways they can interact.
Which sounds like a math nightmare.
It is. Infinities pop up everywhere in the equations. But in the standard model, we have these brilliant mathematical tricks, that's renormalization, to essentially cancel out those infinities so we get usable answers.
But gravity doesn't play nice with those tricks.
No, it doesn't. Because gravity isn't just a force acting on a stage, it is the geometry of the stage itself, space. If you try to treat gravity as a quantum force acting on a zero-distance point particle, the curvature of space becomes infinite.
The math literally blows up.
It blows up. You get infinity as an answer for every single calculation, which means the theory is useless.
So at the Planck scale, like the tiniest possible resolution of reality, the smooth trampoline fabric of Einstein's gravity violently clashes with the jittery, pixelated nature of the quantum world.
Exactly. To get a theory of everything, those two frameworks have to be married. We need a new theory of quantum gravity.
And for the last few decades, the absolute heavyweight contender for that crown has been string theory.
Oh, string theory was supposed to be the white knight that saved physics.
And the initial pitch is so elegant, you just get rid of the point particles. You say, okay, fundamental particles aren't dots, they are tiny one-dimensional vibrating strings.
Right, and the frequency of the vibration determines what particle it is.
Yeah, an electron is just a string vibrating in one key, and a photon is vibrating in another.
And because it's a string, it has actual length. It's not a zero-dimensional point anymore. That physical length smears out the interaction over a tiny distance, which totally bypasses those nasty infinities we talked about.
The math suddenly works.
It works beautifully. And the absolute best part, one of the natural vibrational modes of these strings looks exactly like a graviton.
The theoretical particle that carries the force of gravity.
Yes. So gravity isn't forced into the theory. It emerges naturally from the geometry of the strings.
It sounds like a home run. I mean, it unites gravity and quantum mechanics perfectly.
Yeah.
So why are we reading an entire text about the failure to find a final theory? Why isn't string theory the undisputed law of the land?
Because string theory made a sort of Faustian bargain. To make the math work, to get rid of the anomalies, those strings need more room to vibrate. Way more room than our universe appears to have. The theory flat out demands extra dimensions.
10 dimensions total, right? 9 spatial and 1 time.
Or 11 if you're talking about M theory.
But we only see 3 dimensions of space. Up, down, left, right, forward, back. Where are the other 6 hiding?
The mathematical claim is that they are compactified. They are curled up into these unbelievably tiny, complex shapes. They're called Calabi-Yau manifolds at every single point in space. They're so small, we just can't perceive them.
Okay, but here's the massive problem the text highlights with that. The specific shape of those curled up extra dimensions determines how the strings can vibrate, right?
Correct.
And the vibrations determine the laws of physics, the mass of an electron, the strength of gravity.
Exactly. The geometry dictates the physics.
But there isn't just one mathematical way to fold up those extra dimensions.
No. There are an estimated 10 to the 500th power different ways to fold them.
10 to the 500. That is a 1 followed by 500 zeros.
It is an incomprehensibly large number, and each one of those folds creates a different universe with completely different physical laws.
This is what the source calls the landscape problem.
Yes. String theory doesn't actually describe our universe. It describes a near-infinite landscape of potential universes, and it has absolutely no mechanism to tell us why we happen to live in this specific one.
It feels like we went from searching for a theory of everything to ending up with a theory of anything.
That is the primary criticism. It is mathematically gorgeous, but it's physically predictively weak. Plus, string theory relies heavily on supersymmetry.
The idea that every matter particle has a heavier force particle partner.
Right, and we built the Large Hadron Collider in part to find those superpartners. We found the Higgs boson, which was a huge triumph for the Standard Model, but we found zero evidence of supersymmetry.
Which kind of leaves string theory floating in the wind a bit. So, if string theory is the front runner that's stumbling, what is the alternative? Loop quantum gravity.
Loop quantum gravity, or LQG, is definitely the main rival, and it takes a radically different approach. It doesn't bother with Hessian dimensions, it doesn't use strings, it focuses entirely on the fabric of space-time itself.
It basically says space isn't smooth at all. It's quantized.
Exactly. It suggests space-time is made of tiny, discrete loops, or spin networks, at the Planck scale. Think of a medieval chainmail shirt.
Okay.
From across the room, it looks like a smooth sheet of flexible metal. But if you walk up close, you see it's actually made of thousands of individual interlocking rings. LQG says space is exactly like that chainmail. There is a smallest possible pixel of space, and you cannot divide it any further.
Then that solves the infinity problem we had earlier.
Yeah.
Because you can never get to a zero distance point. You eventually just hit the bottom of the pixel.
Precisely. It doesn't assume a background stage that particles act on. It literally builds the stage out of quantum rules. But it has its own massive flaw. It has a really hard time recovering the standard physics we already know.
Like electromagnetism.
Right. It's very hard to extract the standard forces from those loops.
So we are at a stalemate, but I want to pivot here because this next section of the source material is what really kept me up at night. The roadblocks. The deeply unsettling idea that even if we fix the math, there are philosophical walls we just might not be able to smash through.
The limits of the quest itself.
Yeah. Starting with the problem of initial conditions.
This is a crucial distinction. It's the difference between the laws of the game and the setup of the board. A theory of everything would give us the laws. It would tell us exactly how the universe evolves from moment A to moment B.
The recipe.
Right. But it cannot tell us why moment A was set up that way in the first place. It doesn't give us the ingredients.
It doesn't tell us why the Big Bang had that specific amount of entropy, or why the expansion rate was tuned exactly the way it was.
And this ties directly into the anthropic principle. When we look around, we observe that the fundamental constants of nature, the strength of gravity, the mass of protons, they seem incredibly finely tuned for life to exist.
Yeah, if gravity were just slightly stronger, stars would burn out way too fast for evolution to happen. If it were slightly weaker, matter would never clump together to form stars at all.
And this brings us right back to the multiverse. If string theory gives us 10 to the 500th possibilities, maybe they all actually exist out there. Maybe there are billions of dead, empty universes, and we are just sitting in the one lucky bubble where the numbers randomly align to allow carbon-based life.
The weak anthropic principle. We see a life-friendly universe simply because if it weren't life-friendly, we wouldn't be here to see it. It's a massive selection bias.
But if that really is the answer, it is devastating for the whole concept of a final theory.
Because it means the numbers aren't derived from some beautiful underlying logic. We can't calculate the mass of the electron from first principles. It's just a random environmental accident.
Exactly. It turns fundamental physics into local environmental science. We just be cataloging the weather of our specific universe, not discovering deep, absolute truths that must be so.
That is deeply depressing for a physicist, I imagine. But the text argues it gets even worse.
Let's talk about the math itself. Let's talk about Gödel. Because I always assume that even if the physics gets messy, mathematics is the bedrock of absolute truth. Kurt Gödel basically dropped a bomb on that assumption in the 1930s with his incompleteness theorems. He proved mathematically that in any logical system complex enough to do basic arithmetic, there will always be true statements that simply cannot be proven from within that system.
Statements that are true, but unprovable. It almost sounds like a Zen koan.
It is a fundamental feature of logic. Now, apply that to physics. If reality is ultimately described by a mathematical system, there might be physical truths, constants, or laws that are absolutely true, but we can never logically derive them from the base axioms of our theory.
So the final theory might be mathematically incomplete by its very definition. We could stare at the perfect equation forever, and we would never be able to mathematically prove it's the only right one.
Exactly. And beyond the math, there is a brutally practical wall, the scale problem.
Right, testing this stuff.
We are arguing about vibrating strings and quantum loops that exist at the Planck length, that is 10 to the negative 35 meters. It is absurdly small.
And to probe things that are that small, you need incredibly high energy.
High frequency means high energy. To build a particle accelerator powerful enough to actually see a string directly, you wouldn't just need something the size of the Large Hadron Collider. You would need a collider roughly the size of the Milky Way galaxy.
I'm pretty sure we can't get the funding for a galaxy-sized machine anytime soon.
It is completely physically impossible for us. Which raises a really uncomfortable question for the field. If a theory can never, ever be physically tested, is it still physics? Or have we just crossed the border into pure metaphysics? String theory is mathematically beautiful, but if it requires a galaxy-sized collider to prove, it might permanently remain philosophy.
Speaking of philosophy, I really want to dig into the section the text has on emergence. Because let's say we find it. Let's say we get the God equation on a t-shirt. Does it actually explain everything? The hardline reductionist view says yes, biology is just applied chemistry, chemistry is applied physics, and physics is just this one final equation.
But we know from observation that isn't really how the world works. We have this phenomenon of emergence. There's a famous essay by Philip Anderson called More is Different. And the idea is that complex systems have properties that simply do not exist in their individual parts.
Like, you can know every single quantum property of an air molecule, but that knowledge will never let you predict a tornado.
Or you can map every single neuron in a brain, but you won't find the concept of justice in there.
Right. It reminds me of the 747 analogy. You can't explain how a Boeing 747 flies just by listing the quantum states of every single atom in the wings. You need entirely new, higher-level laws like aerodynamics that emerge at the macro scale.
Which means a theory of everything might actually be useless for understanding the things we as humans actually care about. Life, ecosystems, society. It provides the alphabet, but it doesn't write the novel.
And that brings us to the absolute biggest mystery in the source text. Consciousness. The hard problem. The text argues that a purely physical theory might miss the observer entirely.
This is what philosophers call the explanatory gap. Physics is incredible at describing structure and function. It deals entirely with objective third-person data, wavelengths, mass, spin, velocity.
Right.
But consciousness is fundamentally subjective. It's first person. Physics can describe the exact wavelength of red light hitting your retina, but it cannot explain the subjective feeling of seeing red.
You can't squeeze a feeling out of an equation about electron spin.
Many thinkers argue you simply can't. If the final theory is purely structural and physical, it completely leaves out the inner life of the universe. And this isn't just a purely philosophical gripe. It crashes right back into hard physics with the measurement problem in quantum mechanics.
Oh man, the measurement problem. The idea that the observer actually affects reality.
Right. In the standard Copenhagen interpretation of quantum mechanics, a particle exists in a wave function, a smear of probabilities, until it is measured. Measurement forces it to collapse into a single, definite state. But the math doesn't define what constitutes a measurement. Is it a mechanical camera? Does it have to be a human eye? Does it require a conscious mind?
And if consciousness is required to collapse the wave function, then consciousness isn't just some accidental byproduct of brain chemistry. It is fundamental to the architecture of reality.
And I should say, most physicists strongly dislike that idea. Science generally wants a universe that runs perfectly well without us looking at it. But a true final theory has to account for the fact that there is a conscious observer asking the question. If it can't explain us, it's not a theory of everything.
It's a theory of everything except us.
Exactly.
Before we wrap up, I have to touch on what I thought was the wildest concept in this whole test, the holographic principle. Because reading this felt like we were crossing into simulation theory.
It is a radical shift. It actually comes from the study of black hole thermodynamics. Stephen Hawking and Jacob Bekenstein made this astonishing realization. They found that the total amount of information or entropy that a black hole can contain is proportional to its surface area, not its volume.
Which is super counterintuitive. Usually if you fill a physical box with stuff, the amount of stuff you can fit depends on the 3D volume of the box.
Right. But for black holes, all the information about what fell in is encoded on the 2D surface of the event horizon. This blew physicists' minds and led to a broader idea. What if our entire 3D universe is actually just a projection of information encoded on a distant, two-dimensional boundary?
Literally like a hologram on a credit card. It looks fully 3D when the light hits it, but the actual data generating that image is entirely 2D.
Yes, and it implies something profound. It implies that at the absolute most fundamental level, reality isn't made of matter. It's not made of strings or loops. It is made of information. Qubits.
So the final theory might not even be a physics equation. It might look more like a computer program.
Or pure information processing logic. It completely shifts the paradigm. We've spent a century looking for fundamental particles, but maybe we should have been looking for bits.
So looking at everything we've covered, we have theories that contradict each other, math that might be fundamentally incomplete, multidimensional landscapes we can't test, and a universe that might just be a giant hologram. Are we just chasing a ghost here?
I think we have to honestly face the possibility of infinite regress. It's like a child's game of asking why. Let's say we find the absolute final physical law. The very next question human beings will ask is, well, why that law and not another one? The law cannot explain its own existence.
It just becomes a brute fact.
Because I said so.
And science hates brute facts. We always want reasons. But at the very bottom of the rabbit hole, there might not be an equation. There might just be mystery.
But the search itself, you would argue the search has immense value, right? Even if we never actually catch the horizon. Oh, absolutely. Look at the modern world. The technology we've built just by trying to peek at the basic rules is staggering. MRI machines, semiconductors, GPS, lasers, they are all byproducts of this pure quest for understanding. But even beyond the tech, it's about our place in the cosmos. We are this tiny, fragile species on a rock, actively trying to decode the source code of reality. That is a noble pursuit, even if we ultimately fail to find the final line of code.
It's the journey, not the destination.
As cliche as it sounds, yes. Because think about it, if we actually found the final answer, if we printed it on that t-shirt and proved it, fundamental physics would essentially end. It's the mystery that keeps the human intellect alive.
I love that. And to end today's deep dive, I want to leave you, the listener, with one final thought inspired by the end of the text. It's a concept called metaphysical naturalism. Basically, the unstated assumption that our entire modern scientific world operates under the belief that absolutely everything in existence can eventually be reduced to and explained by physical laws. But what if that assumption is just a lens we are wearing?
Right. What if reality contains layers, like objective moral value, meaning, or the purely subjective experience of consciousness that simply do not map onto physical mathematics? You can't weigh the concept of justice. You can't measure the angular momentum of love. If those things are real, fundamental properties of the universe, then a purely physical theory of everything will always, by definition, be incomplete.
It would be like trying to fully explain a masterpiece painting by only analyzing the chemical composition of the paint. You'd have all the data, but you would miss the picture entirely.
And that, I think, is exactly why we will always keep looking.
Well, my brain is suitably twisted into a 10-dimensional Calabi-Yau manifold at this point. Thank you for walking us through this labyrinth today.
Always a pleasure to get completely lost in the cosmos with you.
And to you listening, keep asking why, even if the answer turns out to be just another question. We'll see you in the next deep dive.